section 9.4, mathematical induction. So in this section, we're going to study a type of proof. I'm so happy. You're going to be so smart by the end of this video. I am very jealous and excited for future you. So we will look in this entire chapter at sequences and series, kind of terms ordered with each other, and then you have a bunch of terms that finding the next one, the next one, the next one. So let's take that idea and look at summations of terms and see if we can get some predictive intuition and knowledge of what could come next. So the type of proof, love that word, proof. It's so Loctite and sure. The type of proof we're going to study in this section, mathematical induction. So we'll look at this first example to kind of introduce this idea. Of course, the big S means summation. So let's add up the first term, which is 1. So go ahead and add up 1. You get 1. Now let's add 1 plus 3. So our previous sum, let's add 3 to it. We get 4. Now let's add 1 plus 3 plus 5. So our previous sum, 4, you know what you got from adding 1 and 3. So 1 and 3 is 4. The previous sum, adding the next term, 5. 4 plus 5, 9. Now let's add the next term. Of course, you can see we're adding odd integers, odd positive integers. 1 plus 3 plus 5 plus 7. So the previous sum plus the new term 7 to get 16. Now let's add the next term. So add 9. So the previous sum, 16. Add 9, we get 25. So we see 1, then 4, then 9, then 16, then 25. Kind of think to yourself for a moment, 1, 4, 9, 16, 25. What do all of those numbers have in common? Well, 1 squared is 1. S sub 2, 2 squared is 4. S sub 3, 3 squared, 9. 4 squared, 16. 5 squared, 25. So the summation of the first n odd integers, 1 plus 3 plus 5 plus 7 plus 9, plus the definition of an odd integer to n minus 1, and the even integer to n. Take one away, if not. So the sum of the first n odd integers can be theorized as n squared. Alright? Now if you want, you can do this forever, for every odd integer, and you're going to go crazy doing that, okay? Instead, wouldn't it be great if we had a way to prove that this worked for every odd integer without showing for every odd integer? And that proof will be mathematical induction. And it all focuses on the next term. Notice how 3, the next term, added it to the previous sum. 5, the next term, added it to 4, the previous sum. 7, the next term, added it to 9, the previous sum. And 9, added that to 16, the previous sum. So the next term, we're always looking at that. So, when doing a mathematical induction proof, there's a couple of steps. I'm going to break it down on the next page into 3 steps, but this has 2. First, highlighter, 2 green, why not? First, P sub 1 is true. Got to show that works. The first term, equaling the first sum. And then for every positive integer k, the truth of P sub k implies the truth of P sub k plus 1. So if we show it once, that should imply that it happens again. So you need to substitute k plus 1. I don't like that k. That seems off balance. Alright, k plus 1 in for k. And then your summation, s, it's helpful to think of s sub k plus 1, so the next sum, so k plus 1, the next term, the next object, s sub k plus 1 is the next sum. Think of that as s sub k plus a sub k plus 1, so kind of current sum. What do we have? Up here, what we had, up here eventually, what we had was 16. That was the current sum. We added 9. The next term. So it can be helpful to think of your next sum as what we have adding the next term. Okay, so let's go through one of these to kind of see how it works. So 3 steps. I'll break it down into 3 steps. And I'll walk you through this first one, that the sum of the first n odd integers equals n squared. So first, let's prove that it works just once. Up here, is it helpful? What's on the left side of the equal sign to the term? What's on the right side is the sum. So we have the term, we have the sum. So step 1. I want to show that it works just once. So let me write things down over here. I think I'll do that. Step 1. Show that your first term equals your first sum. If we're going to show this formula works all the time, we want to first show that it works at least once, so that we're not completely off our game. Step 2, find what we want. What we want the next sum. So plug in k plus 1 into your sum. Steps 1 and 2, pretty simple. Okay, just have to do this, do that. Step 3 is the real proof part. Where, remember, a proof is they give you some given information. Step 1. They give you the proof statement, really the answer. That's step 2, what we want. Step 3, how do we get from a given to our answer? So add the k plus 1 term. To both sides of your equation. So you see how I have throughout these steps, I have term, sum, term, sum. Okay? It's very important. You initially identify what's what. Terms and sums. Okay, left side that equals term, right side sum. So let's do step 1. Show that the k, the first term, equals the first sum. So 2 times 1 minus 1, just plug in 1 to the term. Does that equal your sum when you plug in 1? Instead of n squared, 1 squared. And 1 equals 1. Good deal. We're not totally off. The first time works. Step 2. What we want. Plug in k plus 1 to your sum. So the n squared, now it's going to be quantity k plus 1 squared. Of course, anything squared means something times itself. So distribute that out, FOIL it, whatever you want to call it. K squared plus 2k plus 1. That's what we want. Alright? Now step 3. Add the k plus 1 term to both sides of your equation. Going back here, see we added in the s sub 2, we added 3 to both sides of the equation. S sub 3 added 5 to both sides. S sub 4 added 7 to both sides. S sub 5 added 9 to both sides. We added the k plus 1 term to both sides. The next term, and that should result in the next sum. K plus 1 is the next, so step 2, the next k plus 1 sum. Adding the next term to both sides should give us what we want. So let's write that down. Just starting with what we have. So s sub k plus 1 equals 1 plus 3 plus 5 plus 7 plus ellipses plus 2k minus 1. Gonna leave some space. K squared plus. Now let's add the next term. So the next term, 2k plus 1 minus 1 and 2 quantity k plus 1 minus 1. So you see how everything in black just copied down from what we had in the initial sum. We turned the n's into k's because. And then in the blue, we added the next k plus 1 next, the next term. The n in the term replaced the n with k plus 1. So what we had right here, then adding the next term to both sides. And once you do that, you're pretty much in the clear. Just do some simple arithmetic. K squared plus quantity distribute 2k plus 2 minus 1 k squared plus 2k. 2 minus 1 is 1. And oh my goodness. Got the same thing in steps 2 and 3. What we want, we got it in step 3 after adding the next term. So, step 1, it works once. Great, we have some validity. Step 2, what we want the next sum. So, step 3, let's do that. Take what we know works, add the next term to both sides. Does the next term added to the current sum equal the next sum? Again, practice makes better. 2 more examples to look at. Try to do them on your own. Check your work with my complete notes online.